nowadays. All right, let's get into this. So I always like to start off the week talking about what we need to do. So if we start here, oh heavens, Betsy Lou. Here we are. You can see we're all the way at the bottom of the this chapter. It's the last week. So we're going to be in week 12 for everything you're going to do this week. If you're looking for the keys, they're going to be in week 12. Let's talk about the week. So today we're going to do states of matter notes. And this is the last new set of notes that we need to do. This is the last thing in the standards that we got to get into this unit. Then on Tuesday, we're going to do what's called the miracle thought. And I'm going to give you a little bit of time to start the review. Wednesday is going to be the day that you're going to have to do the review sheet in class. See if you have any questions, all that kind of good stuff. Thursday, you guys in class are going to burn some food and try to figure out the calories in it like our students did last week. This is your week to do the lab. And then we have our Unit 3 thermochemistry test. So that is everything from the entire unit. And so if you're wondering what that is, if you go back to our class, okay, you can see this is the whole unit. So all the topics. We're talking about the thermochem where we did entropy, spontaneity, endo-exothermic. We're talking Q is equal to MC delta T. You got to be able to do Q to Q calculations. You'll probably see one of those big ones on there as well. So all that kind of stuff you got to be prepared for by this Friday, which is the 13th. And you'll have a big test that day. Okay. So that's kind of what we have coming at us for the rest of this week. So new notes today, activity tomorrow, and then we are going to do some review, and then we'll take a test. Okay, perfect. All right, so let's finish it up with what we need to do. So I have right up here, I have a Bunsen burner, and I have some water. And if I look right now, the water's temperature, oh, that's a pretty number, is 77.0 degrees. 77.0 degrees Celsius. When I light this Bunsen burner underneath here, what's going to happen to the temperature of the water? It's going to go up, right? 77, 78, 79, all that kind of good stuff. Why? Why is the temperature of the water going up, do you think? First of all, let's use a couple of our terms here. Is this here, this Bunsen burner, is that endo or exothermic? An exothermic. If you touch that, it would burn you. It's releasing thermal energy. So it's putting thermal energy into the water. What do you think it's doing to the speed of the particles? Is it making the particles go faster or slower if I'm giving them more energy? Faster. And what a thermometer measures is how quickly things hit it, so it's going to make the temperature go up, right? So I kind of, if you want to paraphrase that, when you put a beaker full of water over a lit Bunsen burner, why does the temperature increase? So take that conversation we just had, you can bullet point a few things. The temperature is going up because it's what's happening to the energy, what's happening to the speed of particles. So it should be going up. Okay. Perfect. So if that were to be a test question, how would you answer it? Going up? So I'll show you. So what I said personally is I said because the molecules of water are gaining energy from the energy released by the Bunsen burner, this increases the kinetic energy of the particles. Faster particles mean higher temp. So however you want to paraphrase that, feeling good. All right. Perfect. Okay. Then we're going to stop and we'll talk about number 2 in a second. So I want to kind of get to a phase change place. But right now, it's going up. It's going up. It's at 92.1, 0.4, 0.5, 0.6, 92.7. So obviously our temperature has gone up. Okay. Then we're going to see what happens on this next one once it starts to boil. Okay. So we're going to leave that to the side. We're going to come back to number 2 in a second. We're going to finish this page of notes, and then we're going to come back. All right. This is not meant to insult anybody's intelligence, anything like that. We just have to make sure that everybody's on the same page with solids, liquids, gases, and some of the temperature changes and things like that, okay? Because sometimes you're like, oh, gas to liquid. I forget what that one is. So we're making sure everybody's on the same page with this lecture. This is a lecture. The standards cover a lot of previous knowledge, and hopefully we go on from there. Okay. So particles in a solid. If I have my little states of matter here, the little guy, particles of a solid. They are very close together, and they simply vibrate in place. Okay. They can't move very much at all. So what we say is that particles are fixed in fixed positions. In fixed positions. I'm going to boil over here. Okay. And they're close together, but they can vibrate in place. So particles in a solid just sit and they vibrate. Okay. They vibrate in place. The interesting thing about a solid is it has a definite shape and volume. You can't change the shape, and I can't squish it together anymore, even if I try. They have a definite shape and a definite volume. Definite shape and volume. Okay, nice. So on the big idea of the kinetic energy scale, this is rather low. The other thing, since we're reviewing for our test, it's also low on the entropy scale. Okay, also rather low on the entropy scale, if you were wondering. If I take my solid and I add a good amount of energy, I can turn it into a liquid. Now you'll see in a liquid, the particles are sliding past each other. They can move a little bit more. Okay, they don't necessarily stay in one place. Oh, you evaporated. You. Oh, so did you. Good fun. Okay, so they're sliding past each other. They can move around. They can do all these different things. So they can slide past one another, basically meaning that they move fast enough to overcome some of their forces of attraction between them. And with a liquid, you can change its shape, but you cannot change its volume. Okay? You can change its shape, but you cannot change its volume. Awesome. So you can pour it into a different container. It will take the different shape of the container, but you cannot change the volume. Okay? The particles can move around, so therefore they have more kinetic energy than a solid, but they're not like going crazy over here. All right. Perfect. All right. In a gas, once I were to take my particles and I were to then put them into a gaseous phase, they can go wherever they want. They can do whatever they want to do. They have a ton of energy. They move independently of each other, independently and rapidly. Independently and rapidly. Independently and rapidly.
I have a question.
Yeah, talk to me.
So if you added liquid to liquid, wouldn't that change the volume?
Yeah, so, okay, I'm saying you can't compress it.
Okay.
I see what you're saying. Like, if you add more of it, sure. But I can't, okay, so here, this is what I'm doing. A gas, I can take it, and then you can compress it. Like compressed air, compressed gases, like a can of spray, things like that. So, yeah, you can add more of it. You can't take its current thing. You can take its current thing, you can change the shape. You can't take the current thing and squish it together anymore. That's how, if you move forward in some chemistry, like hydraulic lifts work, things like that. You can't squish them. The particles are close enough together. Very good. I never thought about it from that angle, but you are right. Okay. Perfect. What a gas does is interesting is that it expands or contracts to fill all the available space. Expands or contracts to fill all the available space. And you can change the shape and change the volume of a gas. So a gas, you can change its shape. You can put it into different containers. The gas is the only thing that the particles are so far away from each other that you can actually compress them. You can actually push them closer together. That's how you get like oxygen tanks, air tanks, things like that. Helium. Okay, if you go to a store that has helium balloons, they have one tank and they fill up lots and lots and lots of balloons like that. That's because you can take the gas particles and you can push them closer together. Okay, Perfect. So we have a lot of energy at this point. We're high on the energy scale, also high on the entropy scale. Perfect. Okay. Now, I want to check in very quickly before we turn the page. I have some ice melting over here, and I have some water boiling over here. I'm going to read a little temperature thing here. My ice is at 2.1 degrees Celsius, and my water is at 100.1 degrees Celsius. We're going to come back to that. We're going to keep this bad boy boiling. We're going to keep that guy melting. Okay, we're going to see if anything happens to our temperature at all. So he's still boiling. We'll turn him up a little bit. Good. Okay, phase changes. Let's talk about phase changes. We obviously have melting there and boiling here. That's two of the phase changes. So in the back, phase changes are when you go from one physical state to another physical state. These are all physical changes. These are all physical changes. Okay. All right. Now, if we are going to start here in a solid, it's supposed to be represented by your ice cube, then we have a liquid, then we have a gas. Okay. If we are adding energy, we're going to the right. Adding energy is going to the right. When a solid turns into a liquid, my ice cubes, they're solid turning to liquids. What are they doing right here? The phase change is called melting. Very good. Again, most of these you probably got, but some of them are a little confusing. When you go from a liquid to a gas, there's actually a few words that you can use. What would you say that this is doing right here? This is boiling. And some people will say, because boiling has to happen at a certain temperature. Okay. Some people will call this boiling, and some people call it vaporizing. Vaporizing is a safer word because it can happen. Everything has to happen at boiling at its boiling point.
Is that the same thing as evaporating?
Yes. So good thing. So there's three words. There's vaporizing, boiling, evaporating. Evaporating we don't really talk about here a little bit, but because evaporation happens when just like the particles on the top get enough energy to go away. So that is another word. Absolutely fantastic. But it's just when one particle at a time gets enough energy to kind of say, okay, I can go off and be by myself. So it doesn't have to happen at any specific temperature. It's just when the top ones gain enough energy to leave. You know that evaporating is very slow, right? Perfect. Good. Great. Love it. All right. So yeah, you can't put evaporate here if you want to. Awesome. All right, let's talk about if we go back down and we actually remove energy. Remove energy. If we remove energy, it's what happens when you go from a gas to a liquid. It's hard. It's what's happening on the outside of this glass right now. What do we call this stuff out here? Starts with a C. Condensation or condensing. Very good. That's when the gas goes to a liquid. Good. And then when I take a liquid and I put it into my freezer, it will freeze into a solid. So you have to be able to label a graph with these types of terms. Again, I think you know them. This is background stuff. But let's check real fast. Okay. We just wrote these temperatures down. This thing is still melting, right? So energy is still going into it from the surroundings. And wouldn't you know, it's still only 2.1 degrees Celsius. Interesting. My boiling water, oh my goodness, still at 100.1 degrees Celsius. I'm still heating this, right? So why isn't the temperature going up anymore? It's got up and it stopped. It's at 100, it's at 100, it's at 100, it's at 100, it's at 100. Let's see if we can't explain that, and then we'll come back and answer this question here. So backs are, I'll make you flip all over the place. A very important thing in science is that when you have a phase change, there is no change in the temperature. I don't care if you're condensing, boiling, melting, freezing, sublimating, I don't care. When there is a phase change, There is no change in temperature. What is happening, okay, is you would see a flat line on a graph. So you guys are going to have to be able to label graphs by the end of the period and also on the quiz. If temperature is up in here, if you are going and moving at an angle, that means you are actually changing temperature. But what happens is you see, whenever you hit a phase change, you see a flat line. That means that temperature is staying constant, even if you're adding energy. Here's another flat line, okay? And so we would have this flat line still 100 degrees, 100 degrees, 100 degrees, 100 degrees. So why is that happening? Even though you're still putting it, we just said it was at 87 or 78 degrees, put energy in it, temperature went up until we hit 100. Now all the energy is going in to make that liquid have enough energy to be able to turn into a gas, which takes a ton of energy to do. Okay? So the reason why is that all the energy is being used to change the state. So you can keep heating it up, but it's not going to get any hotter. The particles are going as fast as they can in the liquid phase. And what you're doing is all the energy you're putting in is allowing them to become a gas. Same thing here. Still at 2.1 degrees because all the energy I'm putting in is not going to heat it right now. All the energy that's going in is going to give those particles that are solid, okay, stuck together. Now any bit of heat you give them allows them to break free and start to be a liquid. Okay? So there is never, never a temperature change when you are doing a phase change. So let's put this all together. Okay? So this is called a phase change graph. This happens to be for water. If it is not at 0 and 100, it's not for water. You have these types of graphs for every material out there. Every material has a boiling and a freezing point, okay, and a melting point. Water is very important, so please take a look on the side. Let's make temperature be in Celsius, and let's have thermal energy added be in joules. So if we're looking at the graph first, temperature's on the y-axis, energy's on the x-axis, and for the first part, we're going to add energy. Okay. First thing I'm going to label, there are two very important temperatures for water. So I want you to go right across from this little A, right across from A. That is going to happen at 0 degrees Celsius for water. And for some reason, my ice is melting at 2.3 in here. I don't really know. Maybe my ice has stuff in it. And we just showed you that the other thing here happens at B happens at 100 degrees Celsius. So you have to remember for water, 0, melt and freeze, boil and condense is at 100. All right, let's talk about it. So the first thing on my graph, if you have water that is below 0, it is in the solid state and the solid can actually warm, okay? So your solid, if you took a look at our freezer, it's at negative 5.4 degrees. So those ice cubes came out at negative 5.4 degrees, and then the ice cubes warmed up until they hit 0. As soon as they hit 0, they started to melt. They started to melt. Now, still at 2.1 degrees, okay? The entire time they're melting, they will stay exactly at the same temperature. So you say melt, 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 melt. See how the temperature is not changing? Boom. Once they all become liquid, then a liquid can warm again. Liquid water on our planet is water between 0 and once it hits 100 degrees, like we had over here, the temperature stops again and it either vaporizes or boils, depending on which word you want to use. They both mean kind of the same thing. So the entire time this was boiling, boil, 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 it will stay at 100 degrees Celsius. Okay. Awesome. And then I'm going to try to show you a little demonstration at the end of the period of how you can heat steam. Once it's completely a gas, you can heat that again. The gas can actually get higher, and we did this a little bit earlier in the week, and we got the gas to about 150 degrees here, and so we'll show you that, which is well over the boiling point. Just to take a moment, this is all adding thermal energy, so these processes are all endothermic. Energy goes into warm, energy goes into boil, energy goes in to melt. Those are endothermic processes. Okay, awesome. Now, let's talk about if it were to be reversed. So if that is added, if I go the other direction, okay, that is where energy will be taken out. So what we're going to do is we're going to go down the graph instead, and we are going to do exothermic processes where we're going to take energy out. Perfect. So we're going down. Let's say we started way up here at 150 degrees with my steam. The steam can then cool. Once it gets to 100, it will stop and condense. Then it is a liquid. My liquid can cool. If you were to put water into the freezer with a thermometer and watch it freeze, the entire time that water, and it's like a lab you can do, I think maybe in like middle school or something, the entire time it's freezing, it will stay at 0 degrees Celsius as the phase change is happening. And then after it's frozen, the solid can then cool one more time. Okay? So the main objective is that when you are changing phase, you have a flat line. Okay, very important. No temperature change. So if you wanted to kind of write it together in a little, what I wrote, why does the temperature of the water stop increasing when the water boils? Well, that's easy. Once the water reaches 100, it's boiling. And all the energy is now going to change that liquid into a gas. It's no longer heating it. It is simply changing the liquid into a gas. So the same thing. This is still point 2.1. All the energy going in is melting it. All that kind of good stuff. Okay, now I just need you to practice some of this because you will see these graphs on your test on Friday. So you have a page. And I'll get my demo ready for the end of the period here. We got about 20 minutes, which is a fantastic amount of time for you to finish this. Using your notes, you can if you'd like, says, and using the following diagram, answer questions 1 through 9. Do you think heat is being added or removed from this substance, and explain how you determine this? Well, this is temperature on this side, and this is time on this side, and it looks like the temperature is going up. So if the temperature is going up, do you think energy is being added or removed? How do you know? On the 2 flat graphs. So you're going to go through and you're going to finish the front and the back of this worksheet while I take attendance of people at home and while I come around and see if you have any questions on phase changes. This is the last thing in the thermochem unit. Okay? I'm going to put the music on quietly. I want you to finish this worksheet front and back. Applying what we just learned.